All right, we are looking at Chapter 11, Testing Claims About Means, specifically 11.2 today. So we're looking at a difference in means. So some learning targets for today. You should be able to state appropriate hypothesis for a significance test about a difference between two means. Determine whether the conditions are met for performing a test of a difference of means. Calculate the standardized test statistic. That'll be we'll talk about it. And our p-val for a test about a difference between two means. And then perform a significance test about a difference between two means. And perform a significance test about a mean difference. So we've seen that a little similar with 10.2 with confidence intervals. And then determine when it's appropriate to use a paired T procedure versus a two sample T procedure. And that will go along with the two different types of performing you see above. So starting off, significance testing for mu1 minus mu2, or a difference between means. So our H naught, our null hypothesis is mu1 minus mu2 is equal to a hypothesized value. A lot of time that hypothesis value is 0 to see, hey, is there just a difference in general? And if it's 0, it might also be rewritten this way. Mu1 is equal to mu2. Our conditions are very similar. We've seen them consistently over, and now it's just with two samples instead of one. So first, random. The data comes from two independent random samples or from two groups in a randomized experiment. The 10% condition is when sampling without replacement, both N1 and N2 have to be less than 10% of the population size. And then the third condition is for each sample, the corresponding, so it's the normal large counts, either for this, and this means for both samples. Both samples either have to come from a normal distribution, both ends have to be larger than 30, both of your sample size has to be larger than 30. And if not, if neither one of those is true, then you have to draw a graph of the sample data that shows no skewness or outliers. So let's look at a problem. It has the mean number of hours Americans work in a week changed. One of the questions on the General Social Survey asked correspondents how many hours they worked each week. Respondents from random samples of employed Americans were recorded for 1975 and 2014, and they are summarized below. So does the data give convincing evidence at the alpha of 0.05 significance level of a difference in true mean number of hours worked per week for Americans in 1975 and 2014. So first thing first, we're going to state appropriate hypothesis and define the parameter. So part one, well, I'm looking to see if there is a difference. So it's 2014 minus 1975 is equal to 0. And since I'm looking to see if there is a difference, I'm not asking is 1 greater than or less than. I just ask, is there a difference? So that's why it does not equal 0. Okay, if it said that 2014 was greater or 2014 was less, then I might have a different alternative hypothesis. And then I need to state my parameters. So mu1 is the true mean hours worked per week by Americans in 1975, and mu2 is the true mean hours worked per week by Americans in 2014. And it's not up, so this is really the state phase. It's not a bad idea to state your alpha level as well in this phase. What question B asks to check the conditions. So we have independent random samples of 764 working Americans in 1975 and 1,501 working Americans in 2014. So these are random and independent of each other. The 10% condition is met because both of those sample sizes is certainly less than 10% of all working Americans in that specific year. But note that we do check both conditions or both samples for it. And then the normal large sample, both N1 and N2 are larger than 30, so we are good on our conditions here. Now, after we do our conditions, we go into the do phase, and part of the do phase is we're finding that standardized test statistic, and it's going to be what we've done all year long, statistic minus parameter divided by standard deviation of the statistic. So since we don't know sigma, we don't know the population um, standard deviation, we are using a t statistic again, and this is the general formula. So assuming the conditions are met, you're going to use this t value and then go from there um, to find your p value. Now, there's two ways to find your t statistic or your t score. The first one is with technology, just straight up, hey, doing the test on here. And the second is by hand. And if you do it by hand, you will use the degrees of freedom, which is you take whatever is the smallest sample size and one minus that to get your degrees of freedom. If you use the calculator, it will use a very specific formula that you do not have to know to find the degrees of freedom. So same example as before, we're actually going to do the calculations now. So the first question is explain why the sample results give some evidence of the alternative hypothesis. Well, the sample mean is 41.91 minus 38.97, which is comes out to 2.94. And that is not equal to 0. So right off the bat, our sample gives us some evidence against the true mean because it's not equal to 0. And where it thought the mean was is it equals to 0. So that's some evidence right there. They want us to calculate our t-score. So t x bar 1, well, x bar 2014 minus x bar 1975 minus um, our mu naught, which is 0, over the respective standard deviations. Find it. This formula should look very familiar to our confidence interval formula for a difference in mean. And basically, we get a t-score of 4.88. So I'll show you if you did it on the calculator. You could go to stat test, and then we're not just doing a t-test because it's a 2 sample. So you want to go 2 sample t-test. You press enter. I have the statistics. I don't have all data points in front of me. So x bar 1 is 41.91. S sub x, so the standard deviation of this is 14.35. And the sample size is 1501. My x bar 2 is 38.97. Standard deviation is 13.13. And the sample size is 764. We're doing a does not equal. And don't worry about the pool. We'll keep it as no. And then calculate. So we see right here our t is the same, 4.88, and our p hat. There's a lot of zeros there, right? So it's 1.15 e to the negative 6. So 1, 2, 3, 4, 5, 116. So same answer there. And as you can see here, your degrees of freedom is 1,660. That's because the calculator is using a formula to find it. For option number 2, you could do this by hand. We'd get our t-score the same way. And then the degrees of freedom, we're going to use 100 because we use the smaller sample size. So the smallest sample size is 764. Do n minus 1 that. So we are really using a degrees of freedom of 763. However, the closest number, we always round down for our degrees of freedom. So the closest number on our table is between 100 and 1,000. We have to round down to use degrees of freedom of 100 here. So with our table B p-value, we end up getting 0.01. And specifically, remember, this is a two-tailed test. So you have to multiply by that probability by 2. The calculator automatically does it for you when you choose for it to be a does not equal. It automatically does it. Part C then is what conclusion would you make? Well, because our p-value is so small, it's less than alpha, we reject H naught. There is convincing evidence for a difference in the true mean of hours worked by Americans in 1975 and 2014. Since this is a two-tailed, that's why they use the word difference and don't say greater than or less than, because they were looking for a difference, just either one. So we kind of did a test all in like separate parts. So this section is just putting it all together. So as long as your conditions are met, to test the hypothesis of mu1 minus mu2 is equal to 0, we're going to use this formula for T star, or for our T score, not our T star. Sorry, T star is a confidence interval. This is our T score. And we want to find the probability by calculating the probability of getting a T statistic this large or larger. So I remember grading the chapter 9 tests, and we struggled with evaluating or talking about interpreting a p-value. It's getting a value of this, whatever our t comes out to, and more extreme. So if it's a greater than, it's that value or more, or if it's a less than, it's that value and less than. But it's always that value and to the extreme. You always have to have an interval when you're calculating the probability of this continuous function. Okay. Um, so larger in the direction of the specified alternative hypothesis. And you either, if you use type 1, option 1 using the calculator, the degrees of freedom is calculated for you. If you use option 2, the smaller of the two sample sizes and -1. So we have this problem. So they're wondering, does increasing the amount of calcium in our diet reduce blood pressure? Examination of a large sample of people revealed a relationship between calcium intake and blood pressure. Such observational studies do not establish causation. Researchers therefore designed a randomized comparative experiment. The subjects were 21 healthy men who volunteered to take part in the experiment. Were randomly assigned to two groups. 10 of the men received a calcium supplement, while the control group received a placebo of 11. This is the reminder that in experiments, the sample sizes do not have to be equal. Just putting that out there. The experiment was double blinded. The placebo pill looked identical. The experiment was, yeah, I read that out of order. But the response variable is the decrease in systolic blood pressure for the 12 weeks in millimeters of mercury. So we have the data below. So this does the data provide convincing evidence that a calcium supplement reduces blood pressure more than a placebo on average. So we are into our state plan do conclude. So in the state, we have our hypothesis. So the null is that the difference is equal to 0. Alternative is it's greater than 0. We think that the calcium is going to the calcium is going to reduce the mean systolic blood pressure, so it's greater than equal to 0. Greater than 0. We then state our two means, our two parameters, and then use our alpha level as well. For the plan phase, the randomness, the 21 subjects were randomly assigned to the calcium or placebo treatment, so we're good there. Since this was an experiment and not a sample of 21 people, we don't have to check our 10% condition. And then for the normal large sample, this sample size is for both groups 10 and 11 is certainly less than 30. We don't know it comes from a normal distribution, so we have to draw a dot plot and state, hey, there are no outliers and no strong skewness. So those are some things you just have to state. And let's get into the do. So I'm going to do this on the calculator how I would do it. So let's turn this on. I'm going to stat edit. I'm going to edit my list. I'm just clearing them all out right now. So 7. This will also give you a chance to follow along and plug this data in. -11, -1. All right. So now when I go into stat, I could you could do one var stat of each one to get this information out. My X bar is 5, my sample standard deviation is 8.74, and then I could do calc one var stat of L2 to get that information out. So I could do this by hand. Um, or just get the t statistic. I'm just going to do the test. I'm going to go over to test, and I'm doing a 2-sample t test. Ooh, and I don't think they said that here. In the plan, oh, they did. I didn't mention it. In the plan phase, make sure you label what type of test you're doing. 2-sample t test, because it will help you find it on your calculator, and also make sure you're doing the right test. So 2-sample t test. Here I do have the data, my L1 and L2, and then our conditions where L1 is greater than L2, I believe. L1 is greater than L2. Pooled no, and then calculate. So you get a T of 1.604. And then if you plug this into the calculator, you get a p-value of 0.0644. All right. Now to conclude, well, here our p-value greater than alpha, 0.0644 is greater than alpha. We failed to reject H naught. The experiment does not provide convincing evidence that the true mean decrease in systolic blood pressure is higher for men like these who take calcium than for men like these who take a placebo. All right. So we do not have evidence to suggest. Then asked us to interpret the p-value. So assuming that we assume our null hypothesis is true, there is a 0.0644 probability of getting a difference in the calcium minus placebo in mean blood pressure reduction for the two groups of, that's our, oh, that was whatever our sample was. That's our mu1, x bar 1 minus x bar 2. So getting that value or greater. I highlighted it again because, like I said, in chapter 9, we struggled with being able to interpret this p-value. So it's that value or greater. Right. We kind of talked about it, but the pool choose no. I'm not going to really worry about that because we just kind of went through a whole problem with it. So you could plug in, if you want to try, you can go back in the video to the work week. So you could plug in this data and plug into your calculator if you want. You're going to continue on going. So I gave this tip in 11.1. I'm going to give it again. The formula for 2-sample t statistic for a test about mu1 minus mu2 often leads to calculation errors by students. Also, the p-val from technology is smaller and more accurate than the one obtained using the conservative method with the B table. So I'm going to suggest that you use the 2-sample t test on the calculator. But if so, make sure you label everything and put everything down in the plan and do phase so that you get enough credit. So I would probably write down like my X bar 1, my X bar 2, my sample standard deviations. So I get that information down. I would definitely write down my t-value, find the p-value, and the degrees of freedom. You better write the degrees of freedom if you're using your calculator, because it that's the one thing that will definitely change between the two problems. And the p-value is specific based on the degrees of freedom. So make sure you write that down. This is just a little bit of information about the pooled or not. So essentially, in this class, we'll never pool the data for um, we won't pool the data for a sample mean, right? We had that combined part in proportions a little bit, so I get where the confusion's going. Here, the whole point is you don't know the variances are equal or not, so we are just not going to pool it. Um, and so you could read this, but it's not super important. The whole idea is just, hey, we're not pooling for um, a difference in means ever, unless you take more stats classes outside of AP Stats here. All right. So the next big thing, just like we did for confidence intervals, you had the difference of mean and then a mean difference. We're going to talk about our mean difference. Um, and it seems very similar to a two sample, the way the data is collected. But if it's a mean difference, it actually turns out to be the calculations end up being a lot like um, a one sample test. So right off the bat, our H and I's, our mu difference, the difference in the means, is equal to some hypothesized value, usually equal to 0. The random 10% in large sample, this is why this test looks a lot more like a one sample than a two sample, because you're doing everything based on the difference in that means. So our 10% condition, there's only one to check. The large counts, there's only one to check. The randomness is just paired data. That's the big difference. The paired data comes from a random sample from the population of interest. All right. And the three ways to get normal such large counts is the same as it always has been. All right. Here's our formula for the mean difference. I don't think understanding the mean difference is hard. I think the part that kids get confused the most on am I supposed to be doing a mean difference, or am I supposed to be doing a difference in means? Um, so that'll probably be more of a focus than here. Um, but this is the formula. It looks very similar. So let's look at this example. We're doing the mean difference always happens when you have some type of pairedness going up. All right, you're directly comparing like subject one with somebody else, right? So there's already some pairing going on. So let's look at this example. Researchers designed an experiment to study the effects of caffeine withdrawals. They recruited 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from coffee, colas, and other substances with caffeine for the duration of the experiment. During one 2-day period, subjects took capsules containing their normal caffeine intake. During another 2-day period, they took a placebo capsule. The order in which the subjects took caffeine and placebo was randomized. At the end of each 2-day period, a test for depression was given to all 11 subjects. Researchers wanted to know whether being deprived of caffeine would lead to an increase in depression. Here's a table to display the data from the subjects. So the big thing here is that these people are already paired up against themselves. Some days they took a placebo, other days they took a caffeine, and that part was randomized. So since they're paired up with themselves, that's kind of how you know it's a paired test. Another way you could say is that you're gonna have to have equal numbers of people here. So thinking back to the last example we did, um, you had 10 in one group, 11 in another. Right off the bat, right there, you know you can't do a paired test because things aren't matched up to pair up against. All right, so that's another way you might be able to tell the difference between a mean difference and a difference in mean. So in our state phase, we're going to state, hey, the difference is 0. Here we're looking if it's greater than 0. And that's caffeine. Oh, placebo minus caffeine in depression test. So we're doing placebo minus caffeine, and we're looking if that's greater than 0. So yeah, they said higher scores show more symptoms of depression. Higher scores. So we're looking at that's why it's placebo minus caffeine. If that number's bigger than 0, then the placebo had higher scores, which meant that they had more signs of depression than the caffeine. And then you have the difference. So whenever you write the mean difference, always write which one you're doing, placebo minus caffeine, so we're on the same page, and then tell us your alpha level. For the plan, state the name, t-test for mean difference. This is an experiment, so we need a randomized experiment, randomized assignment, which they said they did. And since it's an experiment, we don't do the 10% condition. But then we will do the normal size large count. We have 11 here. Our n is 11, so it's not large enough. Um, so n not greater than 30, so we have to come up with a here they did a histogram and they say, hey, there's no strong skewness and no outliers. For the do phase, I'll show you on the calculator. You go into stat edit. Let's go out, let's clear these data points. So I got 5, 5, 4, 3. All right, so I have caffeine in L1, and I'm going to do 16. 5. And 0. So, and then I want to do in my L3, I'm going to go up, press enter. And now I was doing placebo minus caffeine, so I want to do L2 minus L1. Enter. So now the differences are all inside here, L2 minus L1. So when I go to stat test, I'm doing a one sample t-test. So I can just do t-test here, boom. I have the data. I'm looking if, yeah, my mu not 0. My frequency, it is an L3. And I'm looking if this is greater than. So I'm good there. I'm going to calculate. I should get, let's see. It appears maybe I typed my data in wrong. 5, 4, 3. Oh, here we go. This was 1, not 14. 7, 5. So I'm just going to do this again. L2 minus L1. Enter. Boom, let's go stat. Over to test. This is a one sample now. Test in L data, L3. Boom, boom, boom. We're all good there. And that is, now we got the correct answer. So this is why this is the one reason why the calculator could be a little difficult, and why you should write down all this information. Because if I just wrote down, oh, my p-value is blank, and I didn't give any other conditions, they might be like, what happened here? If I wrote all this other stuff down, then they could go ahead and do their own test and see, okay, so they must have just typed it in wrong, and you'd get a lot more partial credit. So I get a t-value of 3.53. My degrees of freedom is 11, or is 10. So 11 minus 1 is 10. And then my p-value is 0.0027. And which is more accurate than um, the table. I'll then conclude because the p-val is less than alpha, we reject H0. We have convincing evidence that caffeine withdrawals increases depression test scores on average for subjects like the one in this experiment. All right. So this is the last section to wrap it up. How do you know, are you doing a pair data or two samples? So two sample T procedures require data that come from independent random samples from the two populations of interest or form two groups. The difference or the pair data comes from a random sample from the or one population of interest in a randomized experiment. So that's one giveaway is like, is it two groups or is it one group? And so the proper inference method does depend on how the data were produced. And I think that's a good thing too, right? Here it's two groups in a randomized experiment. This is just a randomized experiment for that one group also. So here's an example. So before exiting the water, scuba divers remove their fins. A maker of scuba equipment advertised a new style of fin that is supposed to be faster to remove. A consumer advocacy group suspects that the time to remove the new fins may be no different than the time required to remove the old fins. So 20 experienced scuba divers are recruited to test the new fins. Each diver flips a coin to determine if they wear the new fin on their left foot or their and the right foot on their right foot, or vice versa. The time to remove each type of fin is recorded for the diver. So this is going to be a difference, a mean difference, because they're paired together, right? Each person, you can pair their right time with their left time and see which one um, is faster. So it also the data comes from two measurements of the same variable. Here, to study the health of an aquatic life, scientists gathered a random sample of 60 white piranha fish from a tribute, I don't know, of the Amazon River during 1 year. The average length of these fish was compared to a random sample of 82 white piranhas from the same a decade ago. So this is a two sample. You're looking at two separate populations, one from 1 year, one from another. They're two separate populations. Um, And so that's kind of how you can see, hey, we can't pair these up because they're two separate populations. Can a wetsuit deter shark attacks? Deter. Wow, long video we're making here. Deter shark attacks. Our research has designed a new wetsuit with color variations that are suspected to deter shark attacks. To test this idea, she fills two identical drums with bait and covers one in the standard black wetsuit and the other in a new suit. Over a period of 1 week, she selects 16 2-hour time periods and randomly assigns 8 of them to the drum in the black wetsuit, and 8 are assigned to the drum in the white suit. During each time period, the appropriate drum is submerged in water that sharks frequent, and the number of times a shark bites the drum is recorded. Here we have a two sample T procedure. The reason why is the data comes from two groups in a randomized experiment, with each group consisting of 8 time periods in which a drum with specific wetsuit was randomly assigned to be submerged. So you have two groups here, um, and there's really no pairing going on between the two. It's like, okay, either I'm going to throw one drum or the other. Okay. All right, and so that is the end. Like I said, I think the hardest part of this all is the last learning target, determine when it's appropriate to use paired T versus a two sample T procedure. But I think we should be good at the state determine, calculate, and conclude based on it, and actually knowing the difference between the two situations. It's just determining which situation I need to be in. All right.